to the base portion of this topic. So acids, the bases are can be thought of as the opposite, inverted commas, of acids. So the properties which acids exhibit are not the same as that, but not the same as that exhibited by the bases. They are opposite, but they undergo very similar reactions as well to the acids. So let's take a look at what are the reactions that bases undergo. So before we begin, let's again define bases. They are the oxides or hydroxides of metals. So if we take a look here, this is the metal oxide, this is magnesium oxide, this is copper 2 oxide, zinc oxide, magnesium hydroxide, aluminum hydroxide. Notice that all this here are metals. So metal oxides are bases. Right? Metal oxides are bases. And if the base is soluble in water, we call it an alkali. So it dissolves in water to give us hydroxide ions. We call it a alkali. So a very simple example would be NaOH. So Na2O, this is sodium oxide. This is a metal oxide. So this is a metal oxide. It means that it is a base. And because Na2O can dissolve in water to give us NaOH, it can dissolve in water to give us NaOH. Let's balance this equation. We shall put a 2 here. 2 O's, 2 H's, 2 Na's, balanced. So because it can dissolve in water to give us NaOH, we call this an alkali. Right? So metal oxides are bases. If the base is soluble in water, we call it an alkali. Take note, do not confuse these two terms. And from the definition above, NaOH can dissociate to give you Na plus and OH minus ions. Right, so an alkali is a soluble base which dissociates in water to give us the hydroxide ions over here. So here are some of the common bases and common alkalis which we encounter. The one which I already mentioned earlier here, Na2O. So potassium oxide, calcium oxide, or quicklime. This is used to lime fields, farming fields. When you notice this releases OH minus, so if there's a mild acid rain attack on a farm and the soil is too acidic for plants to grow, the farmers can actually use quicklime, scatter over the field. The OH minus produced will neutralize the H plus and adjust the pH back to normal. NH3 ammonia, aqueous ammonia, sodium hydroxide, NaOH, these are common alkalis we see in the lab. And this last one, CaOH2, is also known as lime water. Alright? Okay, so now moving on to the properties of alkalis. They have a bitter taste and they feel slippery and soapy. Your soap, in fact, most of the soap at home, most of the soap contains alkalis. So if you don't believe, go back. When you are bathing yourself today, lick yourself when you have applied, after you have applied soap. You will notice that it is extremely bitter. Right, it's extremely bitter. So why do alkalis feel slippery or soapy? This is because the alkalis by themselves, they are not slippery or soapy, definitely, but the alkalis can dissolve the very, very thin layer of oil on your skin surface. So when it dissolves this very thin layer of oil and fat on the skin surface, you feel that there's less friction when you rub your fingers together. So as a result, you notice this slippery or soapy feeling from touching alkali. So it is not the alkali that is slippery, it is actually the fats or the oils on your hands or your fingers that has been dissolved and reduces the friction when you rub your fingers together. So acids have a pH of less than 7, alkalis the opposite, they have a pH greater than 7. The max pH is 14, and acids turn red litmus paper blue, acids turn blue litmus paper red. So alkalis do the opposite. They turn red litmus paper blue. Okay, so red to blue are alkalis. A good way to remember this is actually Al red to blue. So I use this mnemonic to remember. Ali reads books. So Ali Al stands for alkalis, reads stands for red, B stands for blue. So alkalis turn red litmus paper blue. Universal indicator, it turns it purple or violet depending on the strength of the alkali. Recall what's the color for acids in the universal indicator? It is red or orange. Similar to acids, alkalis can also conduct an electric current. Why? Because they can dissociate in water to give you the mobile ions. So when you have mobile ions, you can migrate to the electrodes. So if you have a plus and minus here, the negative ions can migrate here, positive ions can migrate here, and this migration constitutes the flow of electric current. So alkalis can conduct electricity. This last definition here is actually quite important. The alkalis can react with acids to form salt and water only, and this particular reaction is known as neutralization. So if I have KOH and HCl, I get salt and water. We call this reaction neutralization. Take note, you cannot apply neutralization if it's a acid carbonate reaction. Only if it's an acid base reaction giving us salt and water can then we use the term neutralization. Ammonia and HCl, same thing, it gives us a salt. In this case, there's no water present, but we can still call this a neutralization reaction. Why? Because the ammonia reaction is actually two steps. NH3 actually first reacts with H2O to give us NH4 plus OH minus. And this OH minus then reacts with the acid component to give us H2O and Cl minus. So when I combine these two equations together, what do I get? I have NH3 plus H2O plus HCl plus OH minus, giving us NH4 plus OH minus plus H2O plus Cl minus. So when I cancel the water on this side and this side, and I cancel the OH minus on this side and this side, what I have left is simply NH3 plus HCl, giving me NH4 plus Cl minus over here. So NH3 plus HCl giving us NH4Cl. So the water and the OH minus cancels out on both sides of the equation. Sometimes you may have seen this equation before for aqueous ammonia. So aqueous ammonia, some books or maybe some form of media, they represent aqueous ammonia with this NH4OH, and they call this aqueous ammonia. This is actually absolutely wrong. Okay, this is totally wrong, because aqueous ammonia is not NH4OH. It is simply NH3AQ, and NH3AQ can react with water to give us NH4 plus OH minus. So this is the OH minus which gives rise to the basic properties of ammonia here. For example, in the equation I wrote earlier, NH4 OH minus plus the HCl gives us H2O plus Cl minus. So this is the OH minus from ammonia. It is not NH4OH. This is wrong. Please do not write this. Aqueous ammonia is NH3 bracket AQ. Okay, so the reaction between NH3AQ and HCl AQ gives us NH4Cl in this way. It is not NH4OH. If I were to summarize out the key components of the neutralization reaction, I actually only have left with these ions, H plus, OH minus, giving us water. how in the world did I get this equation out, or what we call the ionic equation? Later on at the back of this topic, we will go into more depth on the derivation of the ionic equation from a common chemical equation. So for now, we will just take note that neutralization reaction is simply H plus OH minus giving us water. So the H plus comes from the acid, OH minus comes from the base, and they react to give us water. So this is the neutralization reaction. Alkalis can also react with ammonium compounds to give us salt, water, and ammonia gas on heating. Without heating, this one actually doesn't take place, or takes place extremely slowly. So when you heat the alkali with ammonium compounds, we have NH3 evolve. So this is the equation. Where did the NH3 come from? It's because the OH minus here reacts with the NH4 plus here. This is the ammonium ion. Take note, NH4 plus is ammonium, NH3 is ammonia. Most commonly confused, they are not the same. So when these two react in the presence of heat, we have NH3 plus water. So this is a gas, and this is lost to the surroundings, and you smell a pungent odor from the ammonia gas. Okay, and because NH3 gas, when dissolved in water, gives us OH minus, we can test for this gas with red litmus paper, which is moist. Why moist? Because we need to have water present to allow the OH minus ions to exist. This next property of alkalis is widely applied in QA. So we add sodium hydroxide, or we add NH3 or equals ammonia to precipitate out some metal ions, and based on the color of the metal ions, we can deduce what is the metal ion present. So for example, if I add sodium hydroxide into copper 2 sulfate here, I will get a blue color precipitate. And this blue color precipitate is actually copper 2 hydroxide. And when I see this blue color, I can immediately deduce that in the original solution there is Cu2 plus present. Okay, the Cu2 plus present. Likewise, when I add ammonia into an aqueous solution containing FeCl3, the ion present is Fe3 plus. I will get a reddish brown precipitate of iron 3 hydroxide. So by seeing this, I know that there's Fe3 plus present. So this reaction is known as a precipitation reaction. Why? Because I get a precipitate form during the reaction. So the precipitate is simply the insoluble salt. Okay. Alright, so now let's move on to checkpoint 3. You can pause the video now to attempt the checkpoint. Continue the video once you are done. Now let's move on to checkpoint 3. Right, simple chemical equations with state symbols. Take note, with state symbols, to show the reaction of a base with an acid and a base with a ammonium chloride with heating. Take note, this is solid, so to write AQ. Dilute HCl will be AQ. So for the first one, we have NaOH with HCl giving us salt and water, and state symbols in. This is AQ, this is AQ, this is AQ, and for water it is liquid. For the next one, we have sodium hydroxide, AQ again. This is solid, this is the AQ. Ammonia is a gas, and water is in the liquid state. So we have the base and ammonium compound giving us salt and ammonia and water. So how do we know there's ammonia being produced? Because we have a ammonium compound here, and the N must balance on both sides. The next three equations are for simple precipitation reaction with state symbols, so we need to know which of the salts formed are soluble or are insoluble in water. So first one, iron 2 nitrate plus aqueous sodium hydroxide. Iron 2 nitrate, it will give us a solid. This is a solid. This is our dirty green precipitate. So we need to write the state symbols in. This is AQ, this is AQ, this is solid, and this is AQ. All nitrates are soluble in water. All compounds of nitrates are soluble in water. All compounds containing Na is soluble in water. All compounds containing nitrates are soluble in water. Next one is zinc 2 chloride with aqueous sodium hydroxide. So we get ZnCl2 plus NaOH giving us ZnOH2 and NaCl. Zinc hydroxide is also insoluble in water. This is a white precipitate. This is soluble in water because this is common salt. This is the base. This is the alkali. So yes, and this is the zinc chloride. So yes, this is aqueous zinc 2 chloride. The last one is aqueous iron 3 sulfate with aqueous potassium hydroxide, giving us iron 3 hydroxide. This is a reddish brown precipitate. This is the reddish brown precipitate. So being a precipitate, this is a solid because it is insoluble in water. All potassium compounds are soluble in water. This is the base, and this is the aqueous sulfate. So it's AQ, AQ, solid, and AQ. To recap on which compounds are soluble or which compounds are not soluble, look through the solubility table. Right, look through the solubility table in the topic of metals or the preparation of salts. Okay, so similar to acids where there's the monobasic, dibasic, and tribasic acids, we also have bases which are monobasic, dibasic, and tribasic. So NaOH, for example, contains one OH minus which could possibly dissociate out. Dibasic acids, calcium hydroxide 2, aluminum hydroxide 3. So basicity of a base, it simply refers to the number of moles of hydrogen ions that is required to react with 1 mole of the base. So NaOH, you only need 1 mole of H plus to give us the water. But for AlOH 3, for complete reaction, we need 3 H plus ions to give us 3 moles of water. Okay, simple. So let's do a quick checkpoint 4 on what are the simple equations to show the dissociation of a dibasic base here, calcium hydroxide. So it's just this, gives us Ca2 plus and 2OH minus. So state symbols in AQ, AQ, and AQ. We now move on to the strength of an alkali. So similar to the strength of an acid, the strength of an acid, it refers to how much dissociated is the acid molecule. So this is the same for alkalis. If I have a strong alkali, it undergoes complete dissociation, and during this dissociation, it gives me the hydroxide ions. So NaOH and KOH, they are strong alkalis because they are fully dissociated in water. The weak alkali, for example, ammonia. This is a reversible arrow. So for every 1 mole of NH3, I do not get 1 mole equivalent of OH minus. I get much less than 1 mole. So as a result, I can say that the ammonia, aqueous ammonia, is actually a weak alkali because it does not form 1:1 of OH minus in water. So here are some common examples which contains alkalis. Antacid here, this is the medicine which you take when you have gastric pain. Gastric pain sometimes is caused by excess acid in your stomach, and your stomach contains hydrochloric acid. So if you have too much HCl, you take some antacid to remove the H plus from HCl. So no H plus, no acidic properties, then your pain will go away. Fertilizers sometimes contains bases. Why? Maybe they need to neutralize the extra acidity in the soil. Your soaps contain bases because bases are very good to be used in dissolving fats, in dissolving dirt. Cement, or this is cement. Cement contains a base as well. Base is mixed in to make cement. Then there are actually many other sources of hydroxides that you commonly encounter every day. Batteries, for example, your Energizer cells, your Duracell cells. Inside there's a electrolyte which actually contains a base. It's likely to be potassium hydroxide. Okay, so let's do a very quick and simple checkpoint 5 to recap your acids and your bases before we move on into the next part of the topic, which is indicators and the pH scale. So pause the video now to attempt this checkpoint. Continue the video once you are done. Alright, so for checkpoint 5, which one of the beakers below represent a corn solution of a weak acid? Corn solution means that you must have a lot of the acid per unit volume. So you have corn equals to number of moles over volume. Number of moles over volume. So you must have a lot of moles in a unit volume. A weak acid is partially dissociated in water to give H plus ions. So if we take a look around here, we have a clustering of ions in B and D, but we observe that in B, most of it exists as H plus and X minus, versus D, most of it exists as HX. So we can conclude that D is the answer because D has the most number of particles per unit volume and most of it is not dissociated. There is only a couple of ions, if you notice here, X minus and H plus. So in which of the following reactions is dilute nitric acid not behaving as an acid? So let's do a quick recap. Acid reactions. We have acid base giving us salt and water. We have acid metals giving us salt and hydrogen gas. We have acid carbonates giving us salt and water and carbon dioxide. And we have the acid and oxides giving us salt and water. So if we scan through these 4 equations here, I have an acid metal reaction giving me salt and hydrogen gas, so this is correct, it's behaving like an acid. I have an acid and a hydroxide here, hydroxide oxides giving me salt and water, so this is correct. I have an acid with a carbonate giving me salt, water and carbon dioxide, so this is correct. And for the last one, I have an acid and a metal, which by right should give me salt and hydrogen gas, but I have a salt, I have NO, and I have water, I have no hydrogen gas. So in this case, dilute nitric acid is not behaving as an acid, so the answer is option D. So in this reaction, what is actually happening? Dilute nitric acid is in fact a very powerful oxidizing agent. Okay, so being a very powerful oxidizing agent, it doesn't undergo a typical acid metal reaction. It oxidizes the copper to something else, and during the reaction I have nitrogen oxide being released as well. So this will be covered more in fact in the A levels. So part 3. Which of the following reactions is the metal oxide not behaving as a base? So if a metal oxide were to behave like a base, it will undergo an oxide acid reaction to give me salt and water. The metal oxide can also react with ammonium compounds to give me salt, water and ammonia gas. So if we look through these 4 equations here, let's start from the bottom. I have a metal oxide and an ammonium compound giving me salt, water and ammonia gas, so this is correct. I have a metal oxide with ammonium compound giving me salt, water and ammonia gas, so this is correct. I have a acid here and a metal oxide giving me salt and water, so this is also correct. And for the first one, I have an acid with a metal oxide. By right, it should give me salt and water. I have salt and I have water and I have chlorine gas here. Aha! So in this case, a metal oxide is not behaving as a base. So the answer is A.